Alright, so now let's finally move on to the next problem, and that's problem 4. And here we're asked, let this sequence right here, P sub n, be a sequence of points determined as in the figure over here. Thus, the absolute value of, this is a distance, just meaning distance. So, thus, distance A, P1 is equal to 1. So you have right here, A, P1 is equal to 1. This distance is equal to 1. A, P1, this is typically how you write distances. And then then the distance Pn plus 1 equals to 2, 2 to the power of n minus 1. That is from here to here is equal to that. Yeah, that's the figure we're given here. So it goes 1, 2, and then, so this is 2 to the 1. This is equals 2 to the 0. This equals 2 to the 2. So each time it's getting bigger, 2 to the 3. So 2 to the n minus 1. So at n equals 1, it's 0. At n equals 2, it's 1, and so on. And then the angle AP, so we have this angle right here, A, PN, and PN plus 1. So PN plus 1 is a right angle, so 90 degrees there. So we're always given it's 90 degrees across there. And we're asked, find the limit as n approaches infinity of PN plus 1. In other words, we want this angle, PN plus 1. So this is the angle that we are asked to solve. Alright, so now let's take a look at the solution. So here I copied and pasted it over here, just to show you that how the triangles go up to n. So we'll go to the nth triangle. So we have this right angle triangle, gets bigger and bigger and bigger, and then we have eventually dot dot dot, eventually to the nth one. I'll draw a line like this, gets super big, and so on. And this is it'd be a right angle. This is A. Yeah, so I'll move it away from this A right here. So from there, so there's the point A. This point is gonna be, notice how each one here, so yeah, each time it extends from P2 to P3 there. So this is gonna be our PN point, and then this is gonna be our PN plus 1, and then we're gonna draw a line all the way across here, and we are asked to solve the angle. Theta is here, is PNA, PN plus 1, so that angle PNA, PN plus 1. And we know that this distance right here, each of these triangles distance is getting bigger and bigger to the point of 2 to the n1. And this distance from here to here, that is our APN, like that. And just note, we can calculate this right here using Pythagorean Theorem. This distance is equal to, put an arrow like this. This is our AP2, like this. This equals 2, and then just recall the triangle, the Pythagorean Theorem. If you have right angle, this is A, this is B, this is C, and you'll have C squared equals to A squared plus B squared. So in this case, what we have is this distance is equal to the square root, that's the hypotenuse, of 1 squared plus 1 squared. That just equals to, well, square root of 2. Well, technically plus or minus, but we always look at the plus. I always write plus minus just because it has some good questions that arise up when you always have this minus sign to deal with. Alright, then continuing further, just note that the hypotenuse of the previous triangle becomes the base of the next one. So here's the hypotenuse over here of this first triangle. That becomes the base. So notice how it becomes the base of this next one. And then the hypotenuse of this triangle becomes the base for this one. Hypotenuse becomes the base for this one, and so on, like that. And using the Pythagorean Theorem, we could write a formula for the square of the length APN. In other words, started from over here. So this AP2, let's write this like this. AP2, yeah, notice here, so the previous hypotenuse becomes the base of this next nth triangle there. So AP2 squared, let's keep it squared so we don't need to deal with square roots every time. So if you square that, that just equals to A squared plus, 1 squared plus 2 squared, 1 squared plus 1 squared for this first one, or A squared plus B squared. So this equals to 1 squared plus 1 squared equals to 1 plus 1. equals to 2. So that's the first one. And then the next triangle, remember, that becomes the base. And then, so then AP3 becomes, well, we know this side is 2. And the next side is just AP2, like that. And then square that. So what we're going to get is AP3 squared is equal to AP2 squared becomes, yeah, so the hypotenuse becomes the base, and then plus our other side, which increases to the 2 to the n minus 1. And this is going to be 2. Then this is going to equal to, well, we know this is 2 plus 2. And this is a square, so 2 plus 2, or 2 plus 4. And I'm not going to solve it, I'll just leave it as that. This becomes 2 plus 2 squared. Just keep it like that. Alright, and then the next one is AP4 squared. This equals to, well, AP3 squared plus, and then the next one is, well, 4. Yeah, so 2 to the 2. I mean, I know that was already 4. It's going to be 2 to the 8. So P4. Yeah, this is going to be right here. Actually, no, that is correct. This one is 4. That's 2 to the, that's 2. I mean, that was this one here. 2 squared, like that. And then this one's going to be 2 to the 2. And then we're going to square that. Yeah, because that was a distance. So the next distance is going to be 4 squared. Oh, yeah, I'll do that here. So the 2 squared, 4 squared. And this is the same thing as writing, well, plug this inside. 2 plus 2 squared is our AP3 squared. Plus, this is the same thing as writing 2 to the, 2 to the 4. Or better yet, 2 to the 2 squared. Just keep it like that until we can see the pattern. Let's go to the next one. Let's see if we can grasp the next one. AP5 squared is equal to AP4 squared plus, well, it's going to be 8 squared. Because we have that right here, 8 squared. So we have AP5 equals to AP4. So AP4 plus this. And we're doing the squares because we're doing Pythagorean Theorem. So this equals 2, and we know this throws it over there, this throws it in there, this throws it in there, and so on. And this becomes 2 plus 2 squared plus, this next one is, yeah, let's write it again, 2 to the 2 to the 2 plus, this is 2 to the 3. 2 to the 3, and then this is squared. And then what I'll do is dot, 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 all the way to the nth one. So APN squared. And that's over here, APN squared at distance. This equals. All right, and yeah, so this one's going to equal 2 APN minus 1 squared. And then plus, and then this one becomes, notice how this setup is. Yeah, each one, so 2 to the 3. And then squared, that's we're going to have to subtract by 2. So this is 5, 3, this is 4, 2, and so on. This becomes, this is 2 to the n minus 2 squared. And if we write this part all out, this first part is going to be, well, 2 plus 2 to the squared plus 2 to the 2 squared plus 2 to the 3 squared plus all the way up to plus, yeah, plus, well, this actually just lines up, actually. Look at this one here. So this is 2 to the 1, and then 2 plus 2 to the 2. I mean, yeah, or, yeah, you could consider it as yeah, actually, yeah, this is just 2 to the 1, and then it goes 2 to the 2, 2 to the 2 squared, 2 to the 3 squared, and it's all perfectly in line. So in other words, we could just add this last part to it. 2 to the n minus 2 squared. And now notice what we have here. Instead of dealing with 2's, you could write it as 4. So we could write this as 2 in the first one. And the next one, 2 to the squared, is going to be just 4. And then this next one's going to be, well, 2 squared is 4, but then you have a squared. And now for over here, we could just switch up this this 3 with this 2. So we'll have 2 to the 2 to the power of 3. And that just becomes 4 to the 3. And you could see this because, well, 2 to the 3 power of 2, this just equals to, well, just using the power rules, This equals to 2 to the 6. It's equal to the 6, and the same thing as writing, well, 2 to the 2 times 3. Or you could write it as 2 to the 3 times 2. And yeah, you could just take the 2 squared. 2 squared, 3. This equals to 4, 3. And anyways, just a bunch of power rules there. Alright, so anyway, so we get that, and this goes continually on, plus, 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 all the way here. And then you could, again, replace these two. Replace them, or switch them over. So you'll have 4 to the n minus 2. Alright, here I just moved it over there. And now this whole thing, right, what we have here is a geometric series. Or geometric sum, not a series. Geometric, because it doesn't go to infinity. Geometric sum, or a finite geometric sum. Alright, let's continue further. So we'll go over this. So for n is greater than or equal to 3, a pn, the distance and then squared, forms a geometric sum. So for this part right here, 2 plus, there's a 2 squared, that's a 4. So that's our first part there. So for n is greater than or equal to 3. And then recall from my earlier video on the geometric series and sum. So the geometric series is like this. So summation from n equals 1 to infinity of a to the r a times r to the power of n minus 1, and this equals to a plus ar squared, etc. plus plus. And it's convergent if absolute value of r is less than 1, and its sum is right here, a divided by 1 minus r if r absolute value of r is less than 1. But if absolute value of r is greater than 1, the geometric series is divergent. Note that the above formula is for an infinite geometric series, or just geometric series. That's just the sum going to infinity. But for a finite sum, recall that the formula, or not that, recall the formula below from also that same video. So Sn, the nth partial sum, is equal to a plus ar squared all the way to ar n minus 1. And the partial sum is equal to a times 1 minus r power of n divided by 1 minus r. And when this goes to infinity, if you have a convergent series, this goes to 0. And hence you have this a divided by 1 minus r. If that's, and that's where the r is less than 1. Absolute value of r is less than 1. But just for general, so for the general finite sum, is we write it like this. Since we are not yet finding the limit to infinity, let's apply the finite geometric sum, not infinite series. So we have this, and in our case, what we have is a is r. A is 4, and then it goes from, then it goes r is 4. So r squared, r cubed, etc. So same thing here, a plus ar squared, and it keeps going on and on. So let's write this out. So a p n squared is equal to 2 plus our 4 plus our, and here I'm going to break this apart here. So 4 squared. I'm going to write this as 4 times 4, 1. Then the next one is, the next one's cubed, so I'm going to write 4 times 4 squared. Yeah, so we'll just write this out, 4 times 4 squared, and it keeps going on and on, plus, and the last one is over here, 4n minus 2. Yeah, so we'll take that out, and then it'll be 4n minus 3, so we just subtract 1 there. So 4 times 4n minus 3, like that. So in our case, what we have is, to make it like this geometric sum right here, so this is our going to be our a equals to 4, our r is there, r equals to 4, and a equals to 4, r equals to 4, and now this part right here, our n minus 1, is our n minus 3. So I'll just write this as triple equal sign, just to say that it's replacing our n minus 1. N minus 1 is our n minus 3 there. Alright, so now put this all together. This equals to 2 plus, and then we'll write our formula. A, 1 minus r, n minus, n minus 2. And because notice here, this one is, Sn goes all the way to n minus 1. But the sum has it up to n. So the formula just has it n. So we subtract, so we add 1. So this is n minus 1 plus 1 equals to n. So we have to add 1 to it. So in other words, if this is our n minus 3, that's similar to n minus 1. This has to be our n minus 2 there. And I'll put this in a line right here. This is our equivalent to our r to the n. That's this is equivalent to the n minus 1 there. So, or this part right here, r to the n. And then divide this by 1 minus r. All right, so now we can input our parameters. So 2, and then our a is 4, then 1 minus 4 and minus 2, all over 1 minus 4. And let's simplify this further. I'm going to multiply top and bottom by minus 1, just so we have the bigger numbers positive and the 1 is negative. All right, so this equals 2, and yeah, and this is going to equal to plus 4 times it by 4 and minus 2 minus 1. So we're switching over the negative signs. And now this is a 1 minus 4. That's just a 4 minus 1. Let's put this 4 minus 1 just for completeness. And that becomes a 3. So this equals 2. 2 right there. I'm going to times it by top and bottom 3 over 3. And then plus 4. And let's just keep writing this further. We're actually multiply this inside. This is 4 to the 1, so we're going to add it over to here. So this is going to be 4, and then this is going to be n minus 1, and then minus 4. Then divided by 3. So we have the same common denominator. This equals to 2 times 3 is 6. So what we have is a 6 over 3. Yeah, and solutions method doesn't actually combine them all together, just puts it as 6 over 3 like that. And then separates this one here. I'll just separate those. This becomes, and I'll move this in front. So plus, or I'll actually do that after. 4n minus 1 over 3 minus 4 over 3. So this equals 2. 6 minus 4 is 2. So 2 over 3 minus 4 to the n minus 1 over 3. Like that. And actually I made a mistake. It's not minus, it's a plus. And this equals to our, I'll put this over here, equals to our absolute value, or not absolute, this is just the distance. So the absolute value of the distance, APN squared, like that. So that is what this equals to. All right, so now that we have this, so now that we have the now that we have the lengths of two sides of a right angle triangle, we can calculate the corresponding angle at A. So let's put a bold here. Yes, if we go back up here, so now we know the length right here. We know this, we can solve this just using our tangent. And yeah, I should have stated that earlier, but it's pretty obvious if you think about it. So there is our right angle triangle like this. So we have this length, this is Pn. So there's our point A, there's our angle, there's our Pn plus 1, there's our right angle Pn. We know this side is 2 to the n minus 1. It's going back above, 2 to the n minus 1, as well as in the question Pn plus 1. And then this is APN, we know that now. And this is our APN distance. Alright, so now we know the tangents. Recall tan theta is equal to opposite. Yeah, so opposite over hypotenuse, adjacent. And if the adjacent is the close side, opposite is the opposite side. Equals 2, and then this is our, I'll just put this all together. So this theta is equal to tan, like this, tan of the angle. You can also write it as Pn plus 1. So that just means from Pn A to Pn plus 1. So that's the angle. And now put this all together. This equals 2. And just for even more completeness, this part right here. This equals that 2n, so that 2n minus 1, this just equals to, again, you can write it as put the absolute value out of the way, Pn plus 1, like that. Yeah, so just for completeness, so opposite is equal to the side Pn plus 1 over, I'll just fix that up, and then, write it as here, Pn distance. So that's the opposite. And there's the adjacent, and this equals 2. We know this is 2n minus 1. That's what we're given. And here is our giant formula. Now we're squaring it. We're square rooting it. This is APN squared. So you take the square root plus or minus, but we're obviously going to take the plus. So it's going to be plus, and then 4n minus 1 over 3. like that. So we have that over here. Yeah, so all that together inside. And now we're going to take a limit and so on. But before we even do that, let's just do this first. Yeah, I'm going to write this in the form of this 4n minus 1. So note right here that, yeah, 2n minus 1. So this part right here, simple, just rewrite it out. This equals 2. It's the same thing as writing 2 to the n minus 1 squared and then square root. So we're not changing anything. Just going to get it back and forth. And then what we'll write is equals 2. Yeah, equals 2. And we'll bring this 2 down. So this equals to square root of 2 to the 2n minus 2. Or actually, better yet, do that same thing as before. We'll just take this power and flip it with this one. This equals to 2 to the 2 times by n minus 1. And this equals 2, or I'll keep it over here actually, square root 4n minus 1, like that. Because we have this, and then all square root there. So, and then we're going to replace that over to that one there. So, what we'll have is thus, put it like this, thus, and scroll up. Yeah, so thus, tan theta is equal to, and we'll write this, replace that with 4 and 4 to the power of n minus 1, all square root, and then divide this all by square root 2 over 3 plus 4n minus 1 over 3. And since we're going to take a limit soon, let's multiply top and bottom by this so we can do some cancellations. So 1 times it by 1 divided by 4 to the n minus 1 divided by 1 divided by 4n minus 1. So we're not changing anything again. Let's multiply top and bottom. Alright, so then the top parts cancel. We just have a 1. And then the bottom part, the square root, we can just put that inside. So it's all a giant square root. And let's do this. This is going to be, so when you take the square root, yeah, you just take that out of there. So 2 over 3 times it by, or I'll just put the 2 under, or 2 on top. 2, 3 times 4n minus 1. And then when we bring that inside, this cancels, so we're just going to be left with plus 1 over 3. Alright, so that's what we have there. So thus, limit as n approaches infinity of tan theta equals to limit as n approaches infinity of 1 over square root 2 over 3 times 4n minus 1 plus 1 over 3. And notice this part right here, as it goes to infinity, this is 2 over 3 times it by 1 over 4 to the infinity. So in other words, we're going to have a 1 over infinity, 4 infinity go to infinity, this goes to 0. So this equals to 1 over square root 0 plus 1 over 3. 0 plus 1 over 3. And this equals, alright, and this equals to 1 over, well, we can move the 0, and square root of 1 is just 1, so this can be 1 over square root 3. So 1 divided by 1 divided by square root 3, that's just equals to, bring the 3 on top, square root 3. And now if we just recall our exact trigonometric ratios, and in particular if we look at an equilateral triangle, so instead of just recalling from my earlier video, I'll just derive it now. Yeah, it's pretty much from my earlier video, just it's easy to memorize. Alright, so let's draw this equilateral triangle, and let's say the length is 2. This length is 2, and then put this all the way, cut it down in the middle. This is, yeah, this whole length is, yeah, also 2, but I'm just going to put 1 here, so it's split in half. And remember, a triangle has a 180 degrees or pi total angles. So I'm going to divide this pi over 3. So each one's pi over 3, but then we're cutting this in half. This is going to be our pi over 6, like that. And then this height right here is our square root 3. Now that's from Pythagoras. And again, recall that's just going to be, this is going to be square root, this is going to be equal to, square root, the hypotenuse squared minus the base right here, this squared. So this equals to square root 4 minus 1 equals to square root 3, like that. Yeah, and yeah, so that's square root 3. And notice what we have here. So we have our tan theta limit as n approaches infinity equals square root 3. So in our case, well, we have this right here. So the exact trig ratio, tan pi over 3 is equal to, well, opposite over adjacent equals to square root 3 over 1, which is just square root 3. So in other words, our angle, yeah, so I'll just put this all together. And yeah, put it all together. So thus, the limit as n approaches infinity of the angle PNA to PN plus 1 is equal to pi over 3. Or in other words, 60 degrees. Yeah, this is 60 degrees in degrees or in pi over 3 radians. And we can just box this whole thing like this. And we'll just write this as 60 degrees, like that. Remember this exact trig ratio, 60, 60, and then we'll have another 60, and that will be 180 degrees total. So there's 60 degrees. And yeah, that is that angle right here. PNA, PN plus 1, that's what we were asked. That's the angle.